Hi, so for today we're going to talk about Kirchhoff's voltage law, or more commonly known as the KVL. This is still a video about electrical circuits and more particularly the DC circuits. So what is Kirchhoff's voltage law? Again, Kirchhoff's voltage law states that the algebraic sum of the voltages around any closed path is zero. So if we're going to take the sum of all the voltage drops around the closed path, according to Kirchhoff's, that's equal to zero, according to KVL. So for example, in this circuit, it is a very basic circuit, okay? We have a closed path denoted by, when we go a loop from A to B to C and to D, and it's going around and round, okay? That's a closed loop, okay? So it says that the summation of all the voltage drops or the voltages around the closed loop is equal to zero. That's what the KVL means, okay? So that if we are going to write a KVL equation, so in KVL you will be the one to write those equations, okay? So for example, we arbitrarily selected our flow of current. Obviously, there will be a flow of current inside this closed loop, okay, in clockwise direction, and we called it that again clockwise direction as the conventional current. Okay, so how do we write KVL equations? So for example, if we are to get, okay, the KVL equation around this closed loop ABCD, so what are we going to do is to first, okay, it's important, okay, to consider the signs of the sources, okay, and also consider the sign of the polarity of resistors, even though they don't have polarities, okay. But for the principle of the polarity of resistors, we must say that the current flows from a higher potential, positive, to a lower potential, because if the current starts here, it would enter to the negative supply voltage of V1, and then it would go here. It enters to the left side of the resistor, though resistor has no polarity. So we must label the resistor, since the current enters here on the left side of the resistor, it should be labeled as positive to denote that the current is entering from the higher potential down to the lower potential. Okay, so the polarity of the resistor, okay, it depends on the flow of current, or actually the current. Okay, and if it is arbitrarily selected in the problem, meaning if the problem already states that this is negative and this is positive, you cannot change that. But if it does not have any polarity, okay, you will be the one to actually assign a polarity in that resistor. Okay, of course, following again the rule that the current flows from a higher potential down to a lower potential. So it depends, okay, in the flow of current. So the side that the current would actually enter in the resistor, that is the positive. And the sign that the current leaves the resistor, that's the negative. Because higher potential current, again, flows from higher potential to lower potential. And okay, so how do we write, okay, the KVL equation around this closed loop ABCD? So here's the thing, okay, we can choose any of the elements to start with, but I would like to start with always here on the left side, okay, down to the very right side. Or you can always start, you can also start here, okay, or you can also start here at the resistor, as long as you're consistent with the direction clockwise. So if you start here, then the next thing you're going to write is here, the next thing you're going to write is here, okay. But I would like to start with V sub 1. Of course, as I have said a while ago, it's very important to know the polarities, okay, of the voltage. So for example, V sub 1 is the voltage source here. So if I'm going to start having a closed loop here by applying KVL here, so the current would actually enter on the negative side of the voltage. So if it enters to the negative side of the voltage, I have a negative V sub 1. Remember that this is a voltage drop. So all of the equations of the KVL should be expressed into voltage. okay, it should be expressed into voltage. That's negative V sub 1 because the current enters the negative. Or you can do the both, or you can do the opposite, where the current actually leaves. So it can be positive. But you must be consistent also that if you use positive here, the current leaves the positive, then you should be able to be consistent also that on the next element, you're going to write the sign on which the current lives. Okay? But since we started from where it enters, negative, so all of the elements that we're going to consider as a sign of our voltage should be where the current is entering. Okay? So it enters negative V sub 1. Okay? We continue the loop. Now, the current here is actually enters the positive side of the voltage V sub 2. That's the voltage drop at the resistor. So, this is not the resistor value, but this is the voltage drop on the resistor V sub 2. So, it enters the positive side of the resistor. So, this should be plus V sub 2. Okay? And again, lastly, after it leaves here, okay, the current is actually here and the voltage drop here. This is a current source, but it says what's the voltage drop here, okay, in CD, okay, in the nodes CD or in this branch, okay. So it enters again the negative side of this polarity of this let's say V sub 3. So we have negative V sub 3 is equals to 0. Okay? So this is our KVL equation for this given circuit. And because this is a closed loop, a closed path from A, B, C, D, and going back to A, this is a closed path. The summation of voltage according to KVL or Kirchhoff's voltage law should be equal to 0. Okay, that's how we write KVL equations. For example, of course, if the voltage drops in the resistors are given, okay, and if we have a voltage drop also here, we can find what is the voltage source here. Okay, we have the problem here. We can have some problems like that. Okay, so this is how we write the voltage for KVL for A, B, C, D. Or, as what I have said a while ago, you can also choose, okay, of which we choose here the sign where the current enters. We can also choose the sign where the current leaves the element. Alright, for example, I'm going to write a KVL equation again. So, what I'm going to do is start from voltage 1. The current enters the negative side, but it leaves the positive side. So, I can write positive V sub 1. Of course, if I consider where the current leaves, okay, this element is positive, I should also consider for the other elements around the closed loop. So, I should be consistent. So, if it passed through here, the resistor, so we have positive, it enters the positive, but it leaves with the negative. So I would be having negative V sub 2. And of course, it enters here with a negative sign, voltage drop V sub 3. And it leaves with positive sign. So I would write V sub 3 is equal to 0. So these two equations of KVL are still the same. Okay? But I still practice during my college days that where it enters, that would be the sign. Okay? Rather than where it is. But any notation, you can use it. Okay? As you can see, this is still the same. This equation is still the same as this equation. Okay? If we're going to manipulate those variables, okay? So you will find out that these two are the same. Okay? So let's try an example. So for this figure, okay, calculate the voltage drop V, okay, in the resistor. As we all know, this is a series resistor. By the way, if we have a series resistor, we can always use Kirchhoff's voltage law. But because we know that the current has only one path, so if there are many multiple closed paths in a given circuit, by the combination of parallel and series, we can still apply Kirchhoff's voltage law as long as there is a closed path. Okay, so and the number of closed paths could actually determine how many times you can use KVL. Okay, so for this given series circuit, for example, calculate the voltage drop B in the given figure. Okay, so we have a voltage source, 15 volts. We have a 10 volts here. We are given together with the polarity of the resistor and the voltage drop of the resistor, that is 2 volts. And what we are after is calculate the voltage drop in this resistor. So we can apply Kirchhoff's voltage law by applying it in this loop. Okay, so we start with, okay, the solution is if we have a KVL at loop 1, this is a closed path. Okay, loop 1, we call it KVL at loop 1. Okay, so what will happen is that, again, we start writing the KVL equations. So we start here from 15 volts. So if the current is in this direction by conventional current flow, okay, so what will happen is that it enters the negative 15 volts. So we have negative 15 volts, okay, as it goes. So as we continue the loop, it would enter the positive terminal of the resistor. So we have plus V. It so happened that this is actually what we are trying to find. Okay? Let's label this as V sub 1. Okay? V sub 1 instead of V. Okay? So, and we are going to, after entering here, it's leaving here on the right side of the resistor, it enters again the another voltage source. So we have plus 10 volts. And finally, as it goes here in this direction, it enters the voltage, the right side of the resistor. It happens to be the positive sign, which is correct because the current flows from the higher potential to lower potential. So we have plus 2 volts is equals to 0. Okay, so what are we going to do? We have the summation of the voltages around the closed loop should be equal to 0. So we may be able to solve V sub 1. Okay, so negative 15. So we have negative 15 volts plus 10 volts plus 2 volts is equals to plus V sub 1. Okay, I'm sorry. Plus a V sub 1 is equal to 0. So we can simplify this. So 10 plus 2 is 12 volts. Negative 15 plus 12 volts, that would be negative 3 volts plus V sub 1. And, okay, transposing it to the right side, we have the voltage drop at this resistor V sub 1 is equal to 3 volts. Okay? So that if you're going to plug this 3 volts into this equation, the answer would be 0 because it would not violate the KVL equation. Okay? So that's how we try to solve some simple problems in Kirchhoff's voltage law. So this is a 3 volts. Okay? So that's how we do it. So how about this? Solve the current I. Okay? The current I using KVL and verify your answer using Ohm's law. As we all know, we can get the total current here, okay, the total current I by simply having it in Ohm's law. Okay, so let's try to recall that the total current or the I here, that is equivalent to total current. The current that flows through this resistor, and this resistor are all equal, and that's equivalent to the total current because they're connected in series. So we have that is V sub S, the total voltage source, which is 5 volts, over the total resistance. So if we get the total current, okay, first we use Ohm's law, then KVL. Okay, so the total current would be 5 volts over the total resistance, which is 1 kilo ohm plus 2 kilo ohms, that's 3 kilo ohms. 3 kilo ohms plus 3 kilo ohms, that's 6 kilo ohms. Okay, the total current that we have is 5 over 6 kilo ohms, and that is actually 833.33 times 10 raised to negative 6 amperes. Okay, so or in other words, that's 833.33 microamperes. Your calculator may give you this answer. Okay, 8.333 times 10 raised to negative 4 amperes. That is still correct. This one is equal to this, and these three are all equal to each other. It so happened that this is in engineering notation. You can press the function eng in your calculator, Casio, okay, to have it in engineering notation. Okay, so the current using Ohm's law, the total current I or I sub T is equal to 833.33 microamperes. So how about if we use KVL? So by KVL, since this is a series circuit, so since this form a closed path, we can use KVL. So again, the direction of current is still clockwise. Okay, and then we'll start with the voltage source. So also okay, the current is in this direction, so this we cannot change the polarity because it's given. It's the polarity of the voltage source. But as you can see here, our resistors don't have any polarity. So, what must be the polarity of this resistor 1, resistor 2, and resistor 3? So, if we set the current in this direction, okay, if we follow the current, it enters here. Okay, it has a polarity. We cannot change this. It enters here to the left side of the 1 kilo ohm. So, therefore, we have a positive here and we have a negative here because current, again, flows from the higher potential to lower potential. And for 2 kilo ohms, of course, current enters here on the left side again of the resistor and leaves on the right side of the resistor. And of course, if it enters here, so in 3 kilo ohms, it enters here. So we have a positive sign here and it leaves here. So therefore, we can now write the KVL equation and find the total current using KVL. So what are we going to do is first, we label this the voltage drop at 1 kilo ohm, the voltage drop at 2 kilo ohm, V sub 2, and the voltage drop at 3 kilo ohm. So let's try to write that. So what will happen? We have negative 5 volts. Why? Because it enters the negative side if we are going to make a loop. Okay. Then the next one would be plus V sub 1 because again, continuing the loop, it enters the positive side of the resistor. Then we have plus V sub 2. Okay. And then plus V sub 3. And that is equal to 0 according to Kirchhoff's law. Okay, according to Kirchhoff's law. Okay, so how do we find the current out of this KVL? Okay, by Ohm's law, we know that the Ohm's law is I is equals to V over R, and the one of the formulas to get the voltage is V is equals to IR, and we can apply it on V sub 1 to change this into IR. So we have negative 5 volts plus, okay, the total current, that's the I. The same current flows to the resistor 1, resistor 2, and resistor 3 because they are connected in series. And the voltage drop there should be the current, the total current, multiplied by the resistor 1 because of this formula. So we have 1,000 ohms because kilo means 1,000 plus, okay, I, again, because the current that flows here is the same because they're connected in series in the resistor 2. And of course, that would be I times the resistance. Okay? We simply follow this rule. So this is still voltage. Okay? Because IR is still voltage. And of course, not last but not least, we have 3 kilo ohms plus V sub 3. V sub 3 is equal to I, the same current flows, multiplied by 3,000 ohms is equals to 0. And from that, okay, we can actually find the total current. Okay? The total, I can transpose this on the right side of the equation, the negative 5 volts. So it would become, let's say I drop the unit first of ohms. So I transpose this on the right side. So we have 1,000 I, because 1,000 times I is 1,000 I, plus 2,000 I. Am I correct? Okay. Plus 3,000 I is equals to 5 volts. Okay. I can factor out I because they are common. So we have 1,000 ohms. Okay. That's in ohms. Okay. I did not just write the unit, but these numbers are ohms in resistance. So 1,000 plus 2,000 plus 3,000, okay, is equals to 5 volts. And isolating I by dividing them, 5 volts over the sum of this, 1,000 plus 2,000 is 3,000 plus 3,000 is 6,000. And by the way, what is that? That is in ohms. That is our resistance. So as you can see, 5 volts over 6,000 ohms or 6 kilo ohms, still, I agree that that result should be 833.33 times 10 raised to negative 6. Okay, ampere or 833.33 microamperes. So that should be our answer. So we have verified that in a series circuit, we can use simply the KVL in order for us to get the total current, okay, with the Ohm's law. So it should be the same. It should not differ because we are only using this KVL as another way of solving the current. Okay, I hope you're learning something. Okay, so let's try this last problem. So find V sub 1. Okay, V sub 1 is the voltage drop at the 5 ohms, of which the problem has already selected the signs or the polarity for this 5 ohms. So we cannot change that. We cannot change that. Okay, this is the given. Okay. And the power dissipated at the 10 ohms resistor. What is the power dissipated by this 10 ohms resistor? So we have a voltage source, 30 volts. We have a resistor, 10 ohms. And we have what we call, in a diamond shape, this is what we call a voltage-controlled voltage source. That's correct. VCVS. Voltage-controlled voltage source. This is a voltage source, but its voltage is actually controlled by the voltage drop here. So it depends. This voltage source depends on the what voltage drop we have here in 5 ohms. So this supply voltage, okay, again depends on this voltage drop on 5 ohms. So if the voltage drop is changed here in 5 ohms, definitely the voltage source will be dependent on the change of the voltage drop here in 5 ohms. So this is also called a dependent source. Okay? It depends on the voltage drop here. So we have voltage controlled voltage source. Okay? So, and the voltage drop or the voltage that this supplies in the circuit is 3 times the voltage here at the 5 ohms. So that's what 3V sub 1 means. Okay? And we have here 3 volts and we have 15 ohms. As you can see, if we are going to, again, arbitrarily assign, again, the current in this direction, so we must write the polarity of this 10 ohm resistor and this 15 ohm resistor. We cannot change the polarities given by these sources and even this, okay? But we can only change or we can only assign the current or the polarity for this 10 ohm and 15 ohm. So, as you can see, if we start the loop here, the current would enter here on the left side. So, this would be positive, negative. And as it continues to flow here, okay? So, what will happen? This would be, the current enters here, positive and negative. Now, since this is a closed loop, we can use KVL, okay, by KVL at loop 1, okay, at the loop 1. This is our loop 1, okay. We don't have any other loops because this is a very simple circuit. So what are we going to do? Let's try to solve the KVL, okay. So, is it okay if I'm going to drop the volts here, the volt unit, okay, and I'll write 30 instead of 30 volts, okay? So what will happen? We'll be having, okay, we start here, it enters the negative side, so that's negative 30. I'll drop off the voltage, okay? Okay, is it okay? So what will happen is negative 30, it enters the 10 ohm resistor. Remember that this 10 ohm is not the voltage drop, okay? It is not the voltage drop, okay? It's the resistance. So it enters the positive sign of the resistor. So, but we don't know the voltage drop here. So we can say by using Ohm's law again, V is equals to IR, or the derived formula for Ohm's law, I'm sorry. So this is equal to the current again, because the current that flows here is the same I and it is equal to the total current multiplied by the resistor, which is 10 ohms. Okay. Let me just not rewrite the unit first. Okay. So 10I. Okay, because 10 times the I, that's the voltage drop here. Okay? And then, it enters here on the negative side of this dependent source. So, we have negative 3V sub 1. Okay? That's the voltage drop. Okay? That's actually the source. Okay? And then, we have the current enters here again on the negative side of the resistor. So, we call that negative V sub 1. Because this V sub 1, the problem has already selected that the voltage drop here at 5 ohms is given to be V sub 1. And again, this is negative because it enters the negative side of the resistor. And then as we continue the flow current, will be entering the minus 3, okay, because it enters the negative terminal of the battery. And of course, we have positive plus 15, okay, multiplied by the I, okay. So 15 ohms multiplied by the current, that's the voltage drop here. So, and of course, we have completed the loop that is equal to 0. So, if we are going to simplify this, negative 30, okay. Oh, wait, I'm so sorry. This should be reversed in its polarity. I'm so sorry. This should be positive and negative. So, our equation here would be positive, okay, plus 3 instead of negative 3 because I have a mistake on looking at the given. This should be positive and minus, okay? So, we change again the sign of 3 here. So, instead of negative, it become positive, okay? So, we have negative 30 plus the 3 here, okay? Plus this one, 10i, negative 3v1 minus v1, okay, let me just rewrite though, plus 15i, this is plus 15i, we have negative 3v1, combining like terms, equals to 0, so negative 30 plus 3 is negative 27, 10i plus 15i is 25i, okay, negative 3v1 minus v1, okay, that's negative 4v1 is equals to 0. I can transpose this on the right side. So we have 25i minus 4v1 is equal to 27. Okay, so we are to solve for v1. Okay, but how can we solve that if we don't have the I? So let's see. Okay, let's take note that a VI or V sub 1 is actually what? By Ohm's law, IR, that is equal to I, okay, the current I, okay, current I'm sorry, the current that's correct, the current I multiplied by its resistance, 5 ohms. Of course, okay, we have to consider where the current enters, okay? So the current enters at the negative, okay? So the current here should be negative because it opposes the flow of current. So this should be positive, this should be negative. But since the given is negative positive, we should have a negative 1 here. Okay? Because again, if we plot the current enters on the negative sign. So we should have a negative sign here. So if we substitute that to our V sub 1, again, you have 25i minus 4 times negative 5i. Okay? Because 5 times negative I is negative 5i. We have 27. And we have what? 25i. Okay? Would be plus 20i. The negative becomes positive, negative minus here, and negative here positive, 20i is equals to 27. So 45i is equal to 27, and I is simply 27 over 45, and that is a 0.6 amperes. So we haven't answered any questions, okay? So we have to get V sub 1, but we know that V sub 1 is in the formula. Since we know negative I, so we have V sub 1 is equals to the negative of I, which is negative 0.6 amperes, multiplied by 5 ohms, and that is negative 0.6 times 5 is simply negative 3 volts. So the voltage drop at this V sub 1 is negative 3 volts. How about the power dissipated by 10 ohms? The power dissipated by 10 ohms. So the power dissipated is actually, we can compute it into 3 formulas. Okay, the power dissipated by 10 ohms is actually equal to, since we know I, we can use I squared R formula. So the I squared is 0.6 amperes squared multiplied by the resistance 10 ohms. So we have 0.6 squared times 10, and that is 3.6 watts. And that's all. I hope you learned something in this video. This is a basic KVL in a series of DC circuits lesson. So I'm going to be uploading more circuit videos soon. So please watch my videos, my future videos, and don't forget to subscribe. If you are new to my channel, please don't forget to actually share this to your classmates who are taking engineering course, more specifically electrical circuits. So thank you so much. Again, this is Engineer Abat. Thank you so much for listening, and may God bless you.